Tonight, we drift into the quiet mysteries of the universe. You don't need to follow every word, just let the story carry you, like starlight across a calm sky. This is a place where we can wonder together about the vastness above us, where questions don't demand immediate answers, and where the gentle rhythm of cosmic thoughts might accompany you into rest or contemplation. Imagine yourself lying in a field on a clear summer night. The grass cooled beneath you, your eyes turned upward to the infinite canvas of stars. There is something profoundly peaceful about gazing into that depth, isn't there? The endless expanse of space, stretching beyond our vision, beyond our comprehension. A soft breeze might rustle the leaves of nearby trees, a whisper that seems to echo the question that has haunted humanity since we first looked upward. If space has no edge, what lies beyond it? The night sky presents us with a paradox of sorts of visible infinity. We can see so far, yet we sense there is always more beyond our sight. Like an endless ocean with no shoreline to find, space extends in all directions. The stars scattered across the darkness are like distant islands in this cosmic sea, points of light swimming in an unfathomable depth. When we contemplate this vastness, something in us both trembles and expands. The mind seeks boundaries, edges, shores, yet space offers none that we can discern. Scientists tell us the observable universe extends roughly 46 billion light-years in all directions from where we are. A light-year, the distance light travels in a year, is already an immense measure. Light moves at about 186,000 miles each second, and in 1 year, it travels nearly 6 trillion miles. Multiply that by 46 billion, and the number becomes almost meaningless to our human perception. And yet, even this incomprehensible distance is not an edge, it's merely the limit of what we can observe from our position in space and time. What does it mean for space to have no edge? Perhaps we can consider a simple analogy. Imagine yourself walking forward in a straight line. In our everyday experience on Earth, we expect to eventually reach something: an ocean, a mountain, a wall. But in the cosmos, this intuition fails us. In a universe without boundaries, you could travel forever and never reach an end. Each step forward would bring you somewhere new. Yet you would always remain within the universe, never crossing some final threshold into whatever might lie beyond. There is a certain peacefulness in this thought that we exist within something so vast that it needs no container, no outside, like the surface of a calm lake at night, reflecting the stars above. Space simply is. We float upon it, within it, part of it. The gentle lapping of waves against the shore reminds us that even in vastness there can be rhythm, pattern, meaning. Ancient cultures looked up at the same stars we see today and wondered about similar questions. The Greek philosopher Aristotle imagined the universe as a series of perfect celestial spheres, with Earth at the center and the stars fixed upon the outermost sphere. Beyond this final sphere, he proposed, was the prime mover, the ultimate cause of all motion and change. In this view, space did have an edge, and beyond it was something divine, something other than space itself. Indigenous cultures across the world developed their own cosmologies. Many envisioned the night sky as a dome or tent stretched over the earth, with openings that allowed divine light to shine through as stars. The Navajo saw the stars as the handiwork of Black God, carefully placed in patterns that brought order to the cosmos. The ancient Egyptians imagined the sky as the goddess Nut, her body arched protectively over the earth, with stars adorning her celestial form. These visions speak to our human need to frame the unfruitful, to find boundaries for the boundless. There is comfort in imagining that space ends somewhere, that it has a shape we might eventually comprehend. Yet modern physics suggests a more subtle and perhaps more beautiful reality. As you rest and listen, consider how the question itself shapes our understanding. When we ask what lies beyond the edge of space, we are already assuming that space has an edge and that there is an outside to the universe. But what if these assumptions themselves are products of our limited human perspective? What if the very concept of beyond doesn't apply to the totality of existence? Einstein's general relativity transformed our understanding of space. No longer a fixed, empty stage upon which cosmic drama unfolds, space became an active participant, flexible fabric that curves and warps in the presence of mass. Imagine a vast silk sheet stretched taut. Place a heavy ball upon it, and the sheet curves downward. This is similar to how massive objects like stars and planets curve the fabric of space-time around them. In this understanding, space is not separate from the universe, it is an intrinsic aspect of it. Asking what lies beyond space becomes like asking what lies beyond the surface of a sphere. If you were to travel along the surface of a perfect sphere, you would eventually return to your starting point. Having traversed the entire surface without ever encountering an edge, some cosmologists propose that our universe might have a similar topology, not a sphere exactly, but a shape that curves back upon itself in higher dimensions. In such a universe, you could travel in what seems like a straight line for an immeasurable distance, only to find yourself approaching your starting point from the opposite direction. Like a character in a gentle dream, walking through an endless series of rooms, only to discover they've returned to the first. You would have covered the entirety of space without ever finding its edge. There is something deeply soothing about this possibility, that the universe is complete unto itself, needing no outside, no beyond. Like a perfect circle, it simply is. The beginning contains the end, and the end leads back to the beginning. In meditation traditions, this kind of completeness is often associated with profound peace, with the dissolution of the boundaries that separate self from other, inside from outside. As you continue to rest and listen, notice how your breath creates its own gentle rhythm, in and out, like cosmic expansion and contraction. The air enters your lungs, exchanges with your blood, and returns to the atmosphere. This cycle, so essential to life, has no true beginning or end. It's a continuous flow, one moment leading to the next in an unbroken chain. Perhaps the universe shares this quality of seamless continuity, with no sharp divisions between what is and what isn single quotes, to the paradox of infinity presents itself. When we try to imagine space without an edge, our minds evolved to navigate the finite landscapes of Earth, struggle to comprehend the truly boundless, and yet, within mathematics, infinity is a well-established concept. It's not a number, but a quality, the quality of being without limit. When we say space may be infinite, We're suggesting it continues without end, not that it reaches some specific, albeit very large, size. Consider a simple number line, stretching from 0 and counting upward, 1, 2, 3, and so on. No matter how large a number you reach, you can always add one more. There is no last number. Similarly, in an infinite universe, no matter how far you travel, there would always be more space beyond. Each step forward would take you somewhere a definite location within space, yet you would be no closer to an edge than when you began. This creates a strange contradiction for our spatial intuition. Every point in infinite space is somewhere specific, yet nowhere in particular relative to the whole. You could be at the exact center of an infinite universe, or you could be nowhere near the center, because in infinity, every point can be considered central, like a perfect geometric plane extending forever in all directions. There is no privileged position, no special vantage point from which the entirety could be surveyed. There's a quieting effect in contemplating such concepts. Our everyday worries and preoccupations, so often tied to particular places and moments, seem to dissolve when held against the backdrop of cosmic infinity. If space has no edge, then in some sense, we are always at the center of things, no matter where we are. The universe unfolds around each of us with equal vastness in all directions. Ancient stargazers pondered similar questions as they traced patterns among the stars. For many early cultures, the night sky was a boundary, a solid dome, or a thin veil separating the human realm from the divine. The Greeks called it the celestial sphere, a perfect shell upon which the stars were fixed. When they noticed certain stars, planets wandering across this backdrop, they developed elaborate models to explain these movements while preserving the sphere's perfect form. In medieval Europe, the night sky was often depicted as a series of nested crystalline spheres, with Earth at the center, surrounded by the spheres of the moon, sun, planets, and finally, the sphere of fixed stars. Beyond this final boundary lay the empyrean heavens, the dwelling place of God and the angels. This view provided both a physical and spiritual framework for understanding the cosmos. Space had a definite edge, and beyond it lay something fundamentally different, the divine realm, Islamic. Astronomers during the golden age of Islam made remarkable advancements in understanding celestial mechanics. While working within similar conceptual frameworks, scholars like al-Biruni and al-Tusi developed sophisticated mathematical models that improved upon the Ptolemaic system, yet still conceived of the universe as bounded with a definite structure and limits. Chinese astronomy took a different approach. Rather than emphasizing solid celestial spheres, many Chinese astronomers envisioned the sky as an enormous emptiness, with celestial bodies floating freely within it. The Han Dynasty text Huanenzi describes heaven as a bird's egg, with the earth as the yolk suspended in the center. Yet even this more fluid conception maintained the idea of a boundary, the shell of the cosmic egg. There is something deeply human about this desire to place boundaries around the boundless. We seek edges, not out of limitation, but because edges give shape to our understanding. They help us orient ourselves within the vastness. Like the frames we place around paintings, conceptual boundaries don't diminish what they contain. They help us focus our attention and appreciation as you continue to rest. Imagine yourself as those ancient observers, lying under the same stars that now shine above us. Feel the cool night air against your skin. Hear the gentle sounds of the natural world around you. The questions that stirred in their minds as they gazed upward are the same ones that stir in ours. A continuous thread of human wondering that stretches across millennia. Physics whispers to us now, offering insights that our ancestors could not have imagined. Einstein's general relativity suggests that space itself has properties it can curve, stretch, and bend in the presence of mass and energy. This curvature leads to one of the most fascinating possibilities about the shape of our universe. It may curve back on itself, like the surface of a sphere. Imagine an ant walking on the surface of a perfectly smooth basketball. From the ant's limited perspective, the surface appears flat in any small region. If the ant could walk in what it perceives as a straight line for long enough, it would eventually return to its starting point, having circumnavigated the entire ball. At no point would the ant encounter an edge or fall off the basketball. The surface is finite yet boundless. Similarly, our three-dimensional space might curve in a higher dimension, creating what mathematicians call a closed manifold. In such a universe, light rays sent in a particular direction might eventually return to their source, having traveled around the entire cosmos. Space would have no edge or boundary, yet it would not be infinite, vast from our human perspective. The current observations from cosmic microwave background radiation, the faint afterglow of the Big Bang, suggest that our universe is remarkably flat on large scales. This flatness could indicate that the universe is infinite, extending forever in all directions. Or it could mean that the universe curves so gently that the full circuit would be vastly larger than what we can observe, like a sphere so enormous that any small portion of its surface appears perfectly flat. There's a peaceful symmetry in an idea of a closed universe, a cosmos that contains itself completely, needing no outside, no beyond, like a perfect circle where every point connects to every other through gentle curves. A closed universe would have a profound mathematical harmony. Nothing would be truly separate from anything else. All points would be connected through the very fabric of space itself. As you listen to these thoughts unfold, notice how your mind might drift between understanding and wonder, between following the concepts and simply resting in the vastness they suggest. This drifting is natural, a gentle oscillation between focus and release. The universe itself pulses with similar rhythms, the expansion and contraction of galaxies, the birth and death of stars, the eternal dance of particles coming together and moving apart. Imagine yourself walking through this curved space, following what seems to be a straight path. Step by step, you move forward, passing stars and galaxies, nebulae and clusters. The journey might take billions of years, yet in this thought experiment, time is as boundless as space. Gradually, imperceptibly, your path curves, and then, after an unimaginable distance, you begin to see familiar constellations ahead, the same stars you left behind eons ago. You have walked forever and returned to where you began, yet never found an edge. This dream of cosmic return speaks to something deep within us, longing for completion, for wholeness. Many spiritual traditions describe a similar journey, the soul venturing forth into experience, only to return, transformed yet unchanged, to its source. The Taoist concept of returning to the original nature, the Buddhist wheel of samsara, the Christian prodigal sunal, echo this pattern of departure and homecoming, of journeying outward only to discover that what we seek has been with us all along. Modern cosmology offers a less certain picture. The observed acceleration of the universe's expansion, attributed to the mysterious force called dark energy, suggests that space itself is stretching at an ever-increasing rate. Galaxies distant from our own are moving away faster and faster, carried along by the expansion of the intervening space. If this acceleration continues indefinitely, the universe might expand forever, becoming increasingly sparse and cold. The fate cosmologists call the Big Freeze or heat death. In such a universe, space would indeed have no edge, but it would also have no return. The cosmic journey would be one way, with every path leading ever outward into growing emptiness. There is a different kind of peace in this vision, not the completion of a circle, but the gentle dissolution of all boundaries through endless expansion, like a single note held until it fades into silence. The universe would gradually thin until its music becomes too faint to hear. But even in this scenario, there would be no beyond. Space would continue without end, becoming ever more rarefied, but never terminating at some final boundary. The emptiness itself would be space, not an absence, but a presence stretched infinitely thin. Entropy is the measure of this. Cosmic thinning, the gradual dispersal of energy and order into more uniform, less structured states. The second law of thermodynamics tells us that in any closed system, entropy always increases over time. Order gives way to disorder. Concentrated energy disperses. Patterns fade into randomness. Yet, within this general tendency toward dissolution, local pockets of order and complexity can emerge temporarily. Stars, planets, living organisms, conscious minds contemplating the stars. There is something gently reassuring about this balance between cosmic dissolution and local creation. Even as the universe as a whole moves toward greater entropy, here and there, for a time, beautiful structures arise. Like ripples on a vast, slowly stilling pond, we exist as temporary patterns, local eddies of order in the great flow toward equilibrium. Our very consciousness, this quiet moment of contemplation we share, knows one such eddy, a brief arrangement of matter and energy that creates meaning from the meaningless as you continue to rest, perhaps drifting in and out of sleep. Consider how entropy stretches across the cosmos, gently dissolving the boundaries we crave, the clear distinctions we seek between here and there, between inside and outside, between the universe and what lies beyond. It gradually blur into continuous gradients. The edge we seek may not exist because edges themselves are human constructs, attempts to impose definite boundaries on what is inherently boundaryless. The light from distant galaxies travels through space for billions of years before reaching our telescopes. Some of the most distant objects we can observe are so far away that their light has been journeying toward us since the early days of the universe. And yet, these photons, these ancient messengers from the cosmic dawn, ever encountered a wall, a boundary, an edge beyond which they could not pass. They simply continued through the vastness of space until they happened to intersect with our instruments, allowing us a glimpse of what existed in those remote regions billions of years ago. This continuous nature of light's journey suggests the continuous nature of space itself. A beam of light will travel forever unless intercepted by matter. If space had an edge, what would happen when light reached it? Would it bounce back like an echo from a canyon wall? Would it cease to exist? Would it transform into something else? Our observations provide no evidence for such boundaries. As far as we can tell, light simply continues its journey, crossing ever greater distances as space itself expands beneath it. The most distant light we can observe comes from what astronomers call the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. This radiation has been traveling for roughly 13.8 billion years, since the time when the universe cooled enough for photons to travel freely. When we observe this ancient light, we are looking at what appears to be a wall or boundary, the limit of our observable universe. But this boundary is not an edge of space, itself merely the limit of what we can see from our particular vantage point. It's like standing in a dense fog. Your vision extends only so far in any direction, creating a spherical boundary of visibility around you. Beyond that boundary, the world continues. You simply cannot see it from where you stand. Similarly, beyond the cosmic microwave background lies more universe regions, too distant for their light to have reached us yet. Given the finite age of the cosmos and the finite speed of light, every observer in the universe, regardless of their location, would perceive themselves to be at the center of their own observable sphere. A being on a planet orbiting a star in the Andromeda galaxy would see a different cosmic horizon than we do. Their observable universe would include regions invisible to us, while some areas visible from Earth would lie beyond their horizon. Each perspective is equally valid, equally central, yet limited by the same fundamental constraints of light's finite speed and the universe's finite age. There is a profound humility in recognizing these limitations of perspective. We cannot see the entirety of what exists, yet we can understand why our vision is bounded and appreciate that reality extends beyond what we can directly observe. Like a person standing on the shore of a vast ocean at night, we can see only as far as our light reaches, yet we can know that the waters continue far beyond. Lapping against distant shores we may never visit. As you drift with these thoughts, imagine the countless stars invisible to your eyes, their light traveling through the darkness, perhaps never to be seen by any conscious being. There is a certain quiet beauty in this cosmic privacy. The universe contains more than will ever be observed, holds secrets that will never be revealed. Like the depths of the human heart, space keeps some mysteries hidden, allowing them to exist without being known. Space itself, as Einstein revealed, is not merely an empty stage, but a flexible medium that curves and warps in response to mass and energy. Imagine a vast tapestry, woven of invisible threads, stretching in all directions. The threads themselves are space-time, the unified fabric of space and time that constitutes the fundamental arena of reality. Massive objects like stars and planets create depressions in this fabric, causing nearby objects to follow curved paths. what we experience as the force of gravity. This woven nature of space suggests another way of thinking about our question. If space is a fabric, what lies beyond the fabric? Perhaps this is similar to asking what exists between the threads of a tapestry. At some level, the question dissolves into meaninglessness. The threads don't exist in anything. They constitute the tapestry itself. Similarly, space-time doesn't exist in some larger container. It is the container, the stage, the medium of existence. Some theoretical physicists propose that at the smallest scales far smaller than atoms, or even subatomic particles, space-time might not be continuous, but discrete, composed of tiny units, often called space-time quanta. In this view, space is less like a smooth sheet and more like a finely woven cloth, continuous when viewed from afar, but revealing its granular structure when examined closely enough. These fundamental units of space would be unimaginably small, on the order of the Planck, length about 10 to 35 meters. A scale so tiny that no current technology could hope to probe it directly. If space is indeed woven from such fundamental units, then asking what lies beyond space might be like asking what lies between the threads of the weave. The answer could be simply nothing, not empty space, but the absence of space itself. A concept our space-bound minds struggle to comprehend. As you continue to rest and listen, feel the gentle support of the surface beneath you, your bed, perhaps, or a comfortable chair. This support exists because the atoms in that surface resist being in the same place as the atoms of your body. At the quantum level, this resistance arises from the Pauli exclusion principle, the rule that certain types of particles cannot occupy the same quantum state. This principle gives matter its apparent solidity, creating the tangible world of surfaces and boundaries that we navigate in daily life. Yet, at larger scales, these quantum boundaries blur. The apparently solid surface supporting you is mostly empty space atoms, separated by distances large compared to their size, like tiny solar systems with vast gulfs between them. Similarly, the boundaries we perceive in the cosmos, the edges of planets, stars, and galaxies are merely transitions, places where density and composition change gradually from one state to another. Imagine falling through cosmic silence, never striking a boundary, only drifting deeper. In the void between galaxies, an astronaut would feel no transition, no threshold crossed as they moved from one region of space to another. There would be only the continuous emptiness, punctuated occasionally by the lonely hydrogen atoms that sparsely populate the intergalactic medium. Roughly 1 atom per cubic meter. A vacuum more perfect than any we can create on Earth. In this rarefied emptiness, the distinction between here and there begins to lose meaning. Without landmarks, without variation, distance becomes abstracta, mathematical quantity, rather than a lived experience. An astronaut drifting in such a void might feel suspended in an eternal present, a spaceless space where movement itself becomes theoretical rather than tangible. There is something meditative about this image, the self suspended in vastness, neither arriving nor departing, simply being. Many contemplative traditions speak of similar states of consciousness, the dissolution of boundaries between self and world, the experience of being everywhere and nowhere simultaneously. The Zen concept of mu, the Hindu notion of non-duality, the the mystical experiences reported across cultures and times. All point to a state of awareness where the usual divisions between subject and object, inside and outside, here and there, dissolve into a unified field of pure experience. Perhaps in contemplating the boundlessness of space, we are also contemplating the boundlessness of consciousness itself. Our awareness, like the cosmos it perceives, may have no definable edge, no point where it definitively ends and something else begins. The boundary between what we know and what we don't know is not a sharp line but a gradual fading, a gentle transition from the familiar to the mysterious. Philosophers across the ages have grappled with these questions of infinity and boundary. The ancient Greek philosopher Zeno proposed paradoxes that highlighted the conceptual difficulties of infinite divisibility. In his famous dichotomy paradox, he argued that before you can travel a certain distance, you must first travel half that distance. But before you can travel that half, you must travel a quarter of the original distance. This process of halving continues infinitely, suggesting that any journey requires completing an infinite number of ever smaller steps, a seemingly impossible task. Yet we move through space continuously, crossing these infinite subdivisions without difficulty. The resolution of Zeno's paradox came millennia later, with the development of calculus and the mathematical understanding of convergent infinite series. It turns out that an infinite number of ever smaller steps can indeed sum to a finite total, a concept that helps us understand how continuous motion through seemingly infinitely divisible space is possible. Medieval philosophers, like Thomas Aquinas, considered whether infinity could actually exist in the physical world, or whether it was merely a potential something that could be approached but never reached. Aquinas argued that actual infinity could exist only in the mind of God, while the physical universe must be finite. The notion of an infinite universe seemed, to many medieval thinkers, to infringe upon divine uniqueness only. God could be truly infinite in the modern era. Philosophers like Immanuel Kant proposed that space and time are not features of reality itself, but structures imposed by the human mind to organize experience. In Kant's view, space is not a property of things as they exist in themselves, but rather the form through which we perceive them. This suggests that questions about what lies beyond space may be fundamentally misconceived. They assume space is a thing contained within some larger context, rather than a mode of perception that makes experience possible in the first place. Contemporary philosophers of physics engage with these questions in light of modern cosmology and quantum theory. Some argue that our universe may be just one among many in a vast multiverse, with our space being merely a region within a much larger and more complex reality. Others suggest that the concept of beyond may not apply at the cosmic scale, that space may be complete unto itself, requiring no outside context for its existence. As you rest and reflect, consider how these philosophical visions, infinite versus finite, bounded versus boundless, contained versus containing, reflect our longing for completion. Is the infinite a real place, as some philosophers suggest, or only the shape of our thoughts? Perhaps it is both a concept we use to frame our understanding, yet also a genuine feature of the reality we inhabit. There is a certain comfort in recognizing that these questions have engaged human minds for thousands of years. Your contemplation now connects you to a long lineage of thinkers who have gazed at the stars and wondered about the nature of space and boundary. In asking these questions, you participate in a conversation that spans cultures and epochs, shared human endeavor to comprehend the incomprehensible, the symmetry of space. How a universe without edges reflects our longing for completion reveals itself in both physical theories and philosophical reflections. In mathematics, symmetry refers to features that remain unchanged under certain transformations. A circle is symmetrical because it looks the same no matter how you rotate it around its center. Similarly, the laws of physics exhibit symmetries. They remain the same regardless of position, direction, or time. Einstein's theory of relativity is built upon such symmetries. The principle of relativity itself states that the laws of physics should be the same for all observers moving at constant speeds relative to one another. This symmetry, this invariance across perspectives led Einstein to recognize that space and time must be aspects of a unified whole, space-time, rather than separate and absolute dimensions. A universe without edges would possess a profound kind of symmetry. Every point would be equivalent to every other point, with no location enjoying a privileged status as center or edge. This cosmic democracy of positions echoes philosophical and spiritual traditions that emphasize the unity underlying apparent diversity. The Hermetic maxim, as above, so below, suggests that patterns repeat across scales, that the macrocosm of the universe reflects the microcosm of human experience. There is something deeply satisfying about symmetry, a sense of completeness, of everything being in its proper place. When we create art, music, architecture, or mathematics, we often gravitate toward symmetrical forms. The human face, the butterfly's wings, the spiral galaxy symmetry appears throughout nature, suggesting an underlying order, a hidden harmony in the seemingly chaotic world. Perhaps our search for the edge of space reflects this longing for symmetry and completion. We seek boundaries not because we want to be limited, but because boundaries give shape to our understanding. Like the frame around a painting, edges help us comprehend what lies within them. Yet, a truly complete universe might need no frame, no outside context. Its symmetry would be perfect precisely because it has no edge, no special points, no privileged regions. As you continue to rest, imagine space as a perfect sphere, not a physical sphere existing within some larger space, but a conceptual sphere, complete unto itself. Every point on a sphere's surface is equivalent to every other point. There is no center on the surface, no special position. A two-dimensional being living on the surface would find no edge, no boundary, yet the surface would not be infinite, merely finite and boundless. Our three-dimensional space might have a similar quality, curved in a higher dimension we cannot directly perceive. If so, it would be both finite and boundless, having a definite volume, yet no edge or boundary. Like the sphere's surface, it would wrap back on itself, allowing a journey of sufficient length to return to its starting point. This perfect symmetry would eliminate the need for an outside or beyond. The universe would be complete unto itself, needing no larger context for its existence. Quantum mysteries deepen our questions about the nature of space and boundary. At the subatomic scale, particles exhibit wave-like properties, existing not at definite points, but as probability distributions spread across regions of space. An electron orbiting an atomic nucleus, for instance, is better understood as a cloud of probabilities than as a tiny solid particle following a defined path. This quantum fuzziness challenges our intuitive notion of boundary even at the smallest scales. A hydrogen atom doesn't have a sharp edge where the electron cloud definitively ends. Rather, the probability of finding the electron gradually diminishes, with distance from the nucleus theoretically extending to infinity. There is no point at which we can say with certainty the electron is definitely not beyond this radius. Instead, we can only say that beyond certain distances, the probability becomes vanishingly small, yet never quite zero. Similarly, the quantum vacuum, what we might think of as empty space, is not truly empty in the quantum mechanical view. It seethes with virtual particles that momentarily pop into existence and then disappear, borrowing energy from the vacuum itself in accordance with Heisenberg's uncertainty principle. These virtual particles form a kind of quantum foam at the smallest scales, a restless sea of potential from which particles and forces emerge. In this quantum sea of probabilities without shores, the very concept of beyond may lose its meaning. If space itself is fundamentally probabilistic rather than definite, then asking what lies beyond it might be like asking what lies beyond probability, a question that dissolves into meaninglessness when examined closely. Some theoretical approaches to quantum gravity attempts to reconcile quantum mechanics with general relativities suggest that spacetime itself might emerge from more fundamental processes or structures. In these views, space is not a primary reality but a secondary phenomenon arising from interactions among more basic entities. String theory, loop quantum gravity, and causal set theory each propose different fundamental constituents from which spacetime might emerge: vibrating strings, loops of quantized spacetime, or discrete events connected by causal relationships. If space is indeed emergent rather than fundamental, then asking what lies beyond it might be similar to asking what lies beyond temperature. Temperature is not a substance or an object. It's a property that emerges from the collective behavior of molecules. Similarly, space might be a property that emerges from the collective behavior of more fundamental entities, not a thing contained within some larger context, but a pattern of relationships among more basic constituents of reality. As you drift with these thoughts, notice how quantum concepts both challenge and enrich our understanding of boundary and edge. The fuzzy, probabilistic nature of quantum reality suggests that sharp boundaries may be illusions, convenient approximations that help us navigate the world, but not fundamental features of reality itself. Like the gradually fading edge of a shadow, boundaries in the quantum world are matters of degree rather than kind. There is something peaceful in this fading of boundaries, a gentle dissolution of the sharp divisions our minds tend to impose on experience. The Taoist concept of wu-wei, or non-action, speaks to a similar dissolution, a state of being in which the usual boundaries between self and other, action and non-action, dissolve into a fluid, responsive harmony with the natural flow of things. The cosmic horizon represents another kind of boundary in our understanding of the universe, not an edge of space itself, but a limit to what we can observe from our particular vantage point. Light travels at a finite speed, about 186,000 miles per second, and the universe has existed for a finite time, roughly 8 billion years. These two facts create a natural horizon to our observations. We cannot see objects so distant that their light hasn't had time to reach us yet, given the age of the universe. This cosmic horizon is not a physical barrier or boundary. It's simply the limit of what's observable from where and when we are. It's similar to the horizon we see when looking out over the ocean, not an edge of the earth, but merely the limit of what we can see from our height and position. Just as the ocean continues beyond our visual horizon, space continues beyond our cosmic horizon. What makes the cosmic horizon particularly interesting is that it's expanding. As time passes, light from increasingly distant regions has time to reach us, gradually revealing more of the universe. It's as if we're standing in a dark room as a light slowly brightens, revealing more and more of our surroundings as the illumination increases. Yet there's a complication. The universe itself is expanding, with distant galaxies moving away from us at increasing speeds. Beyond a certain distance, what astronomers call the Hubble radius, currently about 14.4 billion light-years, galaxies recede faster than the speed of light due to the expansion of intervening space itself. This doesn't violate Einstein's speed limit because the galaxies aren't moving through space faster than light. Rather, space itself is expanding between them and us. Closing parenthesis. Regions beyond this Hubble radius present a subtle paradox. Light emitted from such distant regions will never reach us, despite traveling toward us at the speed of light, because the expansion of space between us and them outpaces the light's journey. It's like trying to walk up a down escalator that's moving downward faster than you can climb. Despite your best efforts, you never make progress upward. This creates a kind of ultimate horizon, regions of space from which we will never receive information. Despite the universe's continued aging, some regions of space are, in a very real sense, permanently beyond our reach, not because they're beyond some edge of space, but because the very fabric of space stretches between us and them too rapidly for any signal to cross. There is something poignant in this realization that the universe contains places whose light we will never see, whose stories will remain forever untold from our perspective, like distant ships passing in the night, too far apart for their signal lamps to be visible to one another. Portions of our universe exist in mutual isolation, separated not by walls or boundaries, but by the gentle yet inexorable expansion of space itself. This cosmic horizon, then, is not an end, but a veil of distance, hiding what we cannot yet touch and, in some cases, what we will never touch. It reminds us that completeness of knowledge may forever elude us, not because of the limitations of our instruments or our intelligence, but because of the fundamental structure of space-time itself. As you continue to rest, perhaps drifting between wakefulness and sleep, imagine this cosmic veil not a solid barrier, but a gauzy curtain of distance and time, shifting and billowing with the universe's expansion. Behind it lie galaxies and stars, planets, and perhaps living beings, all part of our universe, yet forever hidden from our view. their light travels toward us with perfect fidelity, carrying images and information about those remote regions. Yet that light will never complete its journey, will never reach any observer's eye. There's a metaphor here for human experience as well, the realization that some aspects of reality may remain forever beyond our comprehension, not because they're inherently incomprehensible, but because our position within the cosmos limits what we can observe and know. Like the light from beyond the cosmic horizon, certain truths may be perfectly clear and definite in themselves, yet inaccessible to us due to our particular situation in space and time. A metaphor that might help us comprehend this boundless yet structured universe is that of a dream where rooms open into more rooms, endlessly unfolding. In dreams, we often experience spaces that transform and extend without logical constraint. You might find yourself in a familiar house, only to open a door and discover rooms you never knew existed. These dream rooms might continue endlessly, each opening into another unexpected space, without ever reaching a final boundary or outer wall. This dreamlike quality of endless unfolding without reaching a limit captures something of how we might think about a universe without edges. In both cases, there is no final door, no ultimate boundary beyond which nothing exists. There is only continued expansion, continued discovery, continued unfolding of what was previously hidden or unknown. Dreams also capture the fluid, interconnected nature of cosmic reality. In a dream, distant locations can be mysteriously connected. You might step through a doorway in your childhood home and find yourself on a mountain peak, with no sense of having traversed the intervening space. These dream connections echo theories in modern physics about the potential connectedness of seemingly separate regions of space, wormholes, theoretical tunnels through spacetime that could connect distant regions represent one such possibility, though still speculative and likely requiring exotic forms of matter or energy to stabilize. Wormholes suggest that space might be folded in higher dimensions, creating shortcuts between points that appear vastly separated in our ordinary three-dimensional perspective. The mathematical concept of non-simply connected spaces provides another analogy. Imagine a piece of paper with 2 points marked on it. In the usual flat, simply connected space, there's one shortest path between those points, a straight line. But if you roll the paper into a cylinder, new paths become available. You might go around the back of the cylinder to reach the second point. If our universe has a complex topology, if it's folded or connected in non-obvious ways in higher dimensions, then what seems like a boundless expanse might actually be richly connected, with multiple paths between apparently distant locations. As you rest and listen, allow your mind to wander through these dreamlike possibilities. Imagine space as a vast mansion with innumerable rooms, where each doorway leads to new and unexpected vistas. There is no outside to this cosmic mansion, no final wall beyond which nothing exists. There is only continued exploration, continued discovery, continued wonder at what lies through the next doorway of scientific understanding. Dreams also remind us of the role of the observer in creating meaning and structure. In a dream, spaces exist because you perceive them. They emerge from and dissolve back into consciousness as your attention shifts. Some interpretations of quantum mechanics suggest a similar role for observation in the physical world, that particles exist in superpositions of multiple states until observed, at which point they collapse into definite positions or properties. While most physicists are cautious about drawing too direct a parallel between quantum observation and conscious perception, these ideas do highlight the intimate connection between the observer and the observed in our understanding of reality. The universe we experience is inevitably shaped by how we experience it, by the particular senses and cognitive structures we bring to our observations. Time itself presents another kind of edge or boundary in our cosmic understanding, not a spatial limit, but a temporal one. The universe as we know it began approximately 13.8 billion years ago in the event we call the Big Bang. Before this moment, before even has, meaning in this context, our current physical theories break down. The extreme conditions of temperature, density, and energy present at the very beginning of our universe lie beyond what our current physics can reliably describe. This temporal edge point of our cosmic history raises questions similar to those about the spatial boundaries of the universe. What, if anything, came before the Big Bang? Was there a previous cycle of cosmic existence? Was there simply nothing? Or does the question itself make a category error, like asking what lies north of the North Pole? Some cosmological models propose that our universe may be one of many in a vast multiverse, each universe beginning with its own Big Bang-like event. Others suggest a cyclical cosmos, expanding and then contracting in an eternal sequence of Big Bangs and Big Crunches. Still others propose that time itself began with the Big Bang, making the notion of before meaningless in this context. Time also presents a moving edge, an ever-advancing frontier that separates the determined past from the open future. Each moment brings new actualities, transforming what was once merely possible into what is now definitely real. This advancing edge of time, this continuous creation of the present from the future, may be the only edge we truly experience directly, the only boundary we actually cross in our lived experience. As you continue to rest, feel this gentle movement of time, the quiet transformation of future into past that occurs with each breath, each heartbeat. There is something profoundly peaceful in surrendering to this flow, in recognizing that we are carried along a current that began with the birth of the universe itself and continues into an open future of possibilities. Time itself, though seemingly linear and uniform in everyday experience, becomes warped and flexible in Einstein's relativity. Near massive objects or at high velocities, time flows at different rates for different observers. Two synchronized clocks will show different times after one has spent time in a stronger gravitational field or moved at high speed relative to the other. This relativity of temporal experience suggests that time, like space, is not an absolute framework, but a malleable aspect of a unified spacetime. Some theoretical physicists propose that at the quantum level, time might be discrete rather than continuous, composed of indivisible units called chronons, rather than flowing in a smooth, unbroken stream. Others suggest that time might be an emergent property rather than a fundamental one, arising from more basic quantum processes that themselves are timeless. These possibilities blur the seemingly sharp edge between past and future, suggesting that the temporal boundary we experience so vividly might be, at a deeper level, as illusory as the apparent edge of the earth at the horizon. Just as the earth has no edge despite appearances, time may have no fundamental direction or arrow. Despite our strong perception of temporal flow, the possibility of other universes has captivated the imagination of cosmologists and science fiction writers alike. Modern theoretical physics suggests several ways in which our universe might be one among many in a vast multiverse. These other universes would not exist beyond our space in a directional sense, not north or south, up or down, left or right of our cosmic neighborhood. Rather, they would exist in ways that transcend our usual spatial concepts. Imagine yourself on a quiet evening, perhaps lying in bed with the gentle weight of a blanket providing comfort as your mind drifts toward these cosmic mysteries. The room around you has its boundaries, walls, ceiling, floor, yet your thoughts recognize no such limitations. In a similar way, our universe may exist alongside countless others, not separated by conventional walls or distances, but by more fundamental distinctions in the very fabric of reality. If you were to hold a soap bubble in your hand and examine its delicate surface, you might notice how it reflects light in iridescent patterns, creating a miniature cosmos of color and form. Now imagine not just one bubble, but many a foam of bubbles, each one complete unto itself, yet touching the others at their boundaries. This image offers us a way to envision one of the most compelling multiverse theories in modern cosmology. The dance of light across these bubble surfaces might remind us of how the night sky appears from Earth, pinpoints of brilliance against darkness, patterns emerging and dissolving as our perspective shifts, just as each bubble in the foam contains its own volume of air, its own internal space governed by the same physical laws, yet separate from its neighbors. So might multiple universes exist, each with its own vast expanse of space and time, perhaps even its own unique physical constants and laws. One multiverse model arises from inflationary cosmology, the theory that our universe underwent a period of extremely rapid expansion in its first fraction of a second. This inflation, driven by an extraordinary form of energy unlike anything we directly observe today, stretched space itself faster than the speed of light. In the span of roughly 10 to 32 seconds, an imaginably brief moment, what would become our observable universe expanded from a volume smaller than a proton to approximately the size of a grapefruit. This expansion smoothed out irregularities and flattened the geometry of space, setting the stage for the more gradual expansion that has continued for the past 13.8 billion years. Imagine the briefness of this inflationary momenta duration, so short that it makes a single heartbeat seem like an eternity. In the time it takes light to cross the width of a single atom, the universe's volume increased by a factor with dozens of zeros after it. This extraordinary stretching of space-time helps explain why our observable universe appears so uniform in all directions, and why its geometry appears so flat, like pulling on the wrinkled fabric of a sheet until it lies smooth and taut. Inflation ironed out the primordial cosmos, preparing it for the billions of years of evolution that would follow. But what if this inflation didn't end everywhere at once? The Russian-American physicist Andrei Lind proposed that inflation might be eternal, continuing forever in some regions while stopping in others, like a vast field where patches of rain fall while other areas remain dry. Inflatito might cease in isolated pockets, allowing matter and energy to condense into the kinds of structures we observe in our universe. Meanwhile, in the spaces between these pockets, inflation would continue, stretching space at an exponential rate. Visualize a piece of bread dough rising in a warm kitchen. As the dough expands, raisins embedded within it move away from each other. Now imagine that the dough continues rising indefinitely, but occasionally small regions stop expanding and begin to form their own separate loaves. These regions where expansion has ceased would be like our universe, places where matter and energy can condense into stars and galaxies rather than being eternally stretched apart by inflation's relentless expansion. That this process would create what cosmologists call bubble universes, regions where inflation has ended, nestled within the greater inflating space like islands in an ever-expanding sea. Each bubble universe would begin with its own Big Bang-like event and evolve according to its own internal dynamics. And because the precise way inflation ends might vary from one bubble to another, these universes might develop with different physical laws and constants. As you rest and contemplate this cosmic foam of universes, imagine the gentle rise and fall of your breath, creating a rhythm that mirrors the expansion and contraction of these cosmic bubbles. Each breath draws in molecules that have existed since the dawn of time, atoms that were forged in the hearts of ancient stars. Your very body connects you to this cosmic history, this unbroken chain of being that stretches back to the earliest moments of our universe. The air filling your lungs contains atoms of nitrogen, have formed in the stellar furnaces of red giant stars billions of years ago. Oxygen atoms released from countless leaves of plants throughout Earth's history. Argon atoms created in ancient supernova. With each breath, you participate in a cycling of matter that connects you directly to the cosmos, a gentle reminder that the boundary between you and universe is more permeable than it might seem. These bubble universes would expand within the greater inflating space, potentially growing to cosmic proportions while remaining forever separate from one another. Like bubbles in a cosmic sea, they might occasionally brush gently against each other, perhaps leaving subtle signatures in the cosmic microwave background, radiation, or other observable phenomena. Some theorists suggest that rare cosmic collisions between bubble universes might leave circular patterns in the background, radiation cosmic bruises that could provide evidence for this multiverse model. Imagine the delicate moment when two soap bubbles touch. Their shared boundary forms a perfect circle, a membrane separating two volumes that remain distinct despite their proximity. Similarly, if two bubble universes were to make contact, they would form a boundary region where the properties of both universes might mingle, creating unusual effects that could, in principle, be detected by sufficiently advanced instruments. Astronomers and cosmologists have searched the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space for unusual circular patterns that might indicate such cosmic collisions. Though no conclusive evidence has yet been found, the spaces between these bubble universes would continue to inflate at an exponential rate, creating ever more volume in which new bubbles could form. This process would have no end. It would be truly eternal, generating an infinite number of bubble universes across an infinite expanse of ever-inflating space. And because the volume of inflating space grows faster than it can be filled with bubble universes, most of reality would consist of this rapidly expanding, energetic medium rather than the matter-filled universes like our own. You were somehow able to transcend the boundaries of our bubble universe, something forbidden by the known laws of physics. What might you experience? Not a wall or an edge in the conventional sense, but a transition into a fundamentally different state of reality. The very laws that govern particle interactions, that determine the strengths of forces and the masses of fundamental particles, might shift. What was solid might become ephemeral. What was stable might dissolve into chaos. The familiar elements that compose our world, hydrogen, oxygen, carbon, iron, might not exist at all, replaced by other configurations of more fundamental entities. Consider how the properties of water change as it transitions between states, from solid ice to liquid water to gaseous steam. The molecular composition remains the same, but the behavior of those molecules, their arrangement and interaction, transforms completely. The transition between universes might involve even more profound transformations, changes, not just in how matter behaves, but in what constitutes matter in the first place, in what forces exist to bind it together, in what principles govern its evolution through time. The boundary regions between bubble universes, if they could somehow be traversed, might be zones of extraordinary strangeness, places where the familiar physics of our universe gradually gives way to something utterly different, like the twilight zone between day and night, between waking and sleeping. These transitional regions would belong fully to neither realm, existing instead as liminal spaces where the foundations of reality itself become fluid and uncertain. Another multiverse concept emerges from string theory, which attempts to unify quantum mechanics and general relativity by proposing that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. Imagine the smallest violin possible, with strings so tiny they make a proton look enormous by comparison. These cosmic strings would vibrate at different frequencies, and each frequency would correspond to a different type of particle: an electron, a photon, a quark. The symphony of these vibrations would create the matter and energy that compose our universe. The elegance of this concept lies in its unifying power. Just as the various notes played on a violin string are not separate entities, but different vibrational modes of the same physical object, the apparently distinct particles of the standard model electrons, quarks, photons, and so on would be different vibrational patterns of the same fundamental strings. The rich diversity of the physical world would emerge from the harmonies and melodies played out by these strings at the smallest scales of existence. String theory works mathematically only in higher dimensional spaces, typically requiring 10 or 11 dimensions rather than the 4 dimensions 3 of space. one of time we directly experience. This requirement initially struck many physicists as implausibly complex, a step away from the elegance they sought in fundamental theories. Yet, as the theory developed, this high dimensionality revealed itself as a potential source of remarkable explanatory power. To visualize these extra dimensions, imagine an ant walking along a garden hose. To the ant, the hose presents two dimensions. It can move forward and backward along the hose's length, or it can move around the hose's circumference. From far away, however, we might see only the hose's length, perceiving it as a one-dimensional line. The circular dimension, the hose's circumference, becomes visible only when we look closely enough. Similarly, the extra dimensions required by string theory might be curled up so tightly that they remain invisible to our experiments, detectable only through their effects on the particles and forces we can observe. Picture yourself lying still, perhaps with eyes closed, aware of your ability to move in three spatial dimensions, forward and backward, left and right, up and down. These dimensions are expansive, extending far beyond the limits of your personal experience. Now imagine that at every point in this three-dimensional space, there exist additional dimensions curled up into tiny geometric shapes, too small to be directly perceived yet, fundamentally affecting how particles and forces behave in the larger dimensions we can navigate. The extra dimensions required by string theory are often imagined to be compactified, curled up into spaces too small to detect with current technology. These compactified dimensions would take the form of complex geometric shapes called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xing-Tung Yau. These manifolds can be configured in an enormous number of ways, at least 500 different possibilities, a number so vast it dwarfs the roughly YY atoms estimated to exist in our observable universe. The geometry of these compactified dimensions would determine the properties of particles and forces in the four-dimensional space-time we experience, like the design of a musical instrument determining what notes it can play and how they sound. The specific shape of these extra dimensions would set the parameters of our physical reality, the strengths of forces, the ways in which different entities can interact. A slightly different configuration might yield a universe where electrons are heavier, or electromagnetism is weaker, or entirely new particles exist alongside the familiar ones as you continue to rest. Imagine these hidden dimensions curled within the fabric of space around you, present in every cubic centimeter, yet invisible to direct perception, like the subtle currents of air in a seemingly still room. These dimensions would shape the behavior of matter and energy without announcing their presence in obvious ways. Their influence would be felt in the precise values of particle masses, in the exact strengths of the fundamental forces, in the delicate balance that allows atoms to form and stars to shine. Consider how the strings of a violin, when properly tuned, produce harmonious music, while an out-of-tune instrument creates discord. The precise configuration of these extra dimensions would tune our universe, setting the parameters that determine whether complex structures like galaxies, stars, planets, and ultimately life can form. A universe with slightly different tuning might collapse back into itself moments after its birth, or expand so rapidly that matter never coalesces into stars, or develop chemistry so unlike our own that carbon-based life becomes impossible. Different ways of compactifying these extra dimensions lead to different, effective physical laws in the resulting four-dimensional spacetime. The specific geometry of the compactified dimensions would determine which particles exist, what masses they have, how strongly they interact, and other essential features of a universe's physics. Some string theorists propose that each possible compactification might be realized somewhere in a vast multiverse, creating a landscape of perhaps 10,500 different possible universes, each with its own physical laws and constants. Imagine a vast library containing books with every possible combination of letters. Most volumes would contain meaningless gibberish, but here and there, amid the chaos, would be works of profound beauty and meaning, the collected plays of Shakespeare, the teachings of the Buddha, the equations of Einstein. Similarly, amid the vast landscape of possible universes, most might be sterile or unstable, incapable of supporting complexity. But some, like our own, would have precisely the right parameters to allow for the emergence of structure, diversity, and potentially consciousness. This concept, known as the string theory landscape, suggests that the particular physical laws we observe in our universe are not uniquely determined by fundamental principles, but are instead one possibility among many, perhaps selected through a process analogous to natural selection, or perhaps simply a random realization among countless alternatives. Like finding yourself born in a particular country among the many nations of Earth, we might simply inhabit one universe among the many in the vast landscape of possibility. The string theory landscape offers a potential explanation for the apparent fine-tuning of our universe's physical constants. Constants like the strength of gravity, the mass of the electron, and the energy of the vacuum seem exquisitely calibrated to allow for the formation of stable atoms, stars, and ultimately, life. Change any of these values slightly, and the universe becomes inhospitable to complexity. In the landscape picture, this fine-tuning isn't the result of design or extraordinary coincidence, but a selection effect. We naturally find ourselves in one of the rare universes capable of supporting observers as the night deepens around you and your thoughts drift through these cosmic possibilities. Consider how the string theory landscape might relate to your own existence. The seemingly improbable fact of your consciousness emerging from trillions of cells working in concert, themselves composed of atoms assembled through billions of years of cosmic and biological evolution, might be less miraculous in the context of a multiverse, where all possible configurations of matter eventually occur. Like a winning lottery ticket that seems impossibly lucky to its holder, but inevitable. From the perspective of the lottery system as a whole, our universe's hospitality to life might be rare, but unsurprising within the vast landscape of possibilities. A third multiverse concept arises from the many worlds interpretation of quantum mechanics. In this view, every quantum event that could have multiple outcomes actually results in all possible outcomes, with reality branching into multiple versions that thereafter evolve independently. Imagine dropping a coin that could land either heads or tails. According to the many worlds interpretation, the universe splits into two versions. At the moment the coin lands, one where it shows heads, another where it shows tails. Both versions are equally real, but the observers in each version can only experience their own branch of reality. The gentle flip of a coin seems like a simple, definite event. It will land either heads or tails, and once it lands, the outcome is fixed and unchangeable. Yet, at the quantum level, events behave quite differently. Until observed or measured, quantum systems exist in states of superposition, simultaneously embodying multiple potential realities. The many worlds interpretation suggests that when such a system is observed, reality itself branches to accommodate all possible outcomes, with each branch becoming a complete, self-contained universe, indistinguishable from our own, except for the outcome of that specific quantum event, if true. This would create an unimaginably vast number of parallel universes, each differing from the others in the outcomes of quantum events throughout cosmic history. Some of these universes would be nearly identical to our own, perhaps differing only in the position of a single subatomic particle. Others would diverge more dramatically, perhaps stars formed in different patterns, or life evolved along different paths, or fundamental constants varied slightly due to quantum fluctuations in the early universe. As you continue to rest and listen, allow your imagination to wander through this quantum multiverse. Perhaps in one branch of reality, you decided to listen to music instead of this narrative. In another, you might be watching the stars from a different location. In still others, the entire history of Earth might have unfolded differently. Dinosaurs might never have gone extinct, or humans might never have evolved, or technological civilization might have taken a dramatically different course. The quantum realm reveals itself not through our direct senses but through carefully designed experiments that probe the behavior of the very small. The famous double-slit experiment, for instance, shows that particles like electrons behave sometimes as discrete entities and sometimes as waves of probability, depending on how they're observed. When not directly measured, an electron passing through two parallel slits creates an interference pattern, as if it had gone through both slits simultaneously. When observed more directly, it appears to go through exactly one slit, like a tiny bullet. This wave-particle duality suggests that at the quantum level, reality is fluid, probabilistic, resistant to our classical intuitions about definite positions and states. The many-worlds interpretation was first proposed by physicist Hugh Everett III in 1957, though it wasn't widely discussed or accepted at the time. Everett's insight was that the mathematics of quantum mechanics doesn't actually require the collapse of probability waves that most interpretations assume. Instead, the equations could be taken at face value, suggesting that all potential outcomes of a quantum event actually occur in different branches of reality. Imagine the universe as a vast, ever-branching tree. Each quantum event, each moment when multiple outcomes are possible, creates a new fork in the tree's structure. From our perspective, within one branch, we experience only a single timeline, a single history. But the mathematics suggests that the other branches are equally real, equally valid continuations of the universal wave function. The tree grows endlessly, its branches multiplying with every quantum choice point, creating a structure of incomprehensible complexity and scope. This interpretation resolves some of the paradoxes of quantum mechanics, such as the famous Schrodinger's cat thought experiment, where a cat in a box is simultaneously alive and dead until observed. In the many worlds view, the universe splits into two branches, one with a living cat, one with a deceased one, and observers in each branch experience only their respective outcome. The apparent randomness of quantum measurements isn't truly random, but reflects which branch of reality the observer happens to experience. Consider how this perspective might relate to your own life path. Every choice you've made, every random event that has affected your journey, might have unfolded differently in parallel branches of reality. There might be versions of you leading vastly different lives, pursuing different careers, living in different places, forming relationships with different people. These alternate selves would be as real as you are, experiencing their own joys and sorrows, their own discoveries and disappointments, all stemming from the same origin but diverging through the accumulated effects of quantum branching. The many worlds interpretation doesn't require any change to the mathematical framework of quantum mechanics, simply takes the equations seriously, without adding the extra postulate of wave function collapse. This mathematical elegance appeals to many physicists, though others find the proliferation of unobservable parallel universes too high a metaphysical price to pay for this elegance. As you continue to rest, imagine these parallel universes not as distant places, but as alternate versions of reality that share the same physical space as our universe, separated only by their quantum states. Like radio stations broadcasting on different frequencies, these universes would occupy the same location but remain invisible to one another, their separate realities playing out without interaction or awareness of the others. The branch points between these parallel worlds would not be dramatic moments of cosmic significance, but the accumulated effects of countless tiny quantum fluctuations, the random decay of radioactive atoms, the precise path taken by photons, the quantum uncertainty in the position and momentum of particles. Each moment contains virtually infinite potential variation at the quantum level, creating an ever-branching structure of alternate realities, so numerically vast that it staggers the imagination. Some theorists have suggested that certain quantum phenomena, such as interference patterns in double-slit experiments, might be explained by interactions between parallel universes. The physicist David Deutsch, a prominent advocate of the many worlds interpretation, has argued that quantum computers derive their potential power from performing calculations in multiple universes simultaneously. These speculative ideas remain controversial, but they highlight how the concept of parallel universes has moved from pure philosophy to theories with potential implications. Imagine the quiet room around you filled with ghostly parallel versions of yourself, each slightly different, each following their own version of reality, all occupying the same physical space but forever separated by the unbridgeable gap between quantum states. Like ships passing in the night, these alternate realities would proceed on their separate courses, unaware of one another's existence, yet all stemming from the same fundamental equations, the same universal wave function that encompasses all possibilities. As you continue to rest and listen, imagine these other universes not as distant places we might someday visit, but as alternate realities coexisting with ours, separated not by spatial distance, but by more fundamental barriers, like parallel dreams occurring simultaneously in different minds. These universes would unfold according to their own internal logics, perhaps with their own conscious observers, wondering about the nature of their cosmic boundaries. Feel the gentle weight of your body, the subtle pressure where it meets the surface supporting you. This sensation of weight arises from the gravitational attraction between your mass and Earth's, a force that extends with diminishing strength throughout the cosmos. Every particle in your body is connected through this invisible force to every star and galaxy in the observable universe. In a very real sense, you are not separate from the cosmos, but intimately connected to it through these fundamental forces. The gravitational influence between your body and distant stars is vanishingly small, weak to measure with our most sensitive instruments, yet a gentle tether binding you to the farthest reaches of the observable universe. This connection is not merely poetic, but mathematical, a direct consequence of Newton's law of universal gravitation and Einstein's general relativity. The stars and galaxies and nebulae you might observe in the night sky are not merely objects of beauty and wonder, but active participants in a cosmic web of mutual influence that includes you as one of its countless nodes. There is something both humbling and expansive about these multiverse possibilities. They remind us that reality may be far vaster and more varied than what we can directly observe, like a listener catching fragments of many conversations in a crowded room. We may be perceiving only a tiny portion of a much richer and more complex reality. Our universe, vast as it seems, might be just one note in a greater cosmic symphony, one story among countless being told across the multitude of existence. The limits of our perception shape our sense of reality's boundaries. Consider how different the world appears to a bee, perceiving ultraviolet patterns invisible to human eyes, or to a bat navigating through darkness by echolocation. Our senses evolved to help our ancestors survive on the African savanna, not to perceive the full spectrum of cosmic reality. Our instruments extend these senses remarkably, allowing us to detect radio waves from distant galaxies or the subtle ripples, gravitational waves passing through Earth. Yet even these enhanced perceptions may capture only a fraction of what exists, like a person with a radio that receives only one frequency, missing the countless other stations broadcasting through the same space. Yet even if these other universes exist, they don't constitute an outside or beyond to our space in the usual sense. They wouldn't be located at some distant point we could reach by traveling far enough. They would exist in ways that transcend our usual spatial concepts. The boundary between our universe and others would not be a wall or an edge, but a more fundamental separation, a difference in the very fabric of reality itself. Rather than imagining space as a container that might have an outside, we might instead consider reality as a nested hierarchy of organizing principles, laws and patterns that give rise to the structures we observe. From quantum fields to particles to atoms to molecules to stars to galaxies, each level emerges from the one below it, creating new forms of order and complexity. without requiring any external container or context. Consider a simple analogy. The rules of chess determine what moves are possible on the board, creating the potential for countless different games, strategies, and outcomes. These rules aren't located somewhere outside the chessboard. They're embodied in the very way the game unfolds. Similarly, the laws of physics aren't imposed from outside our universe, but are embedded within its very fabric. In the relationships between its parts, in the patterns of its evolution through time. The boundary of our universe, in this view, isn't a spatial edge, but the limits of applicability of these particular patterns and relationships as you rest. Imagine your consciousness as a similar kind of emergence, not something outside the physical world, but a pattern of organization that arises from the incredible complexity of your brain, like the multiverse emerging from more fundamental principles. Your awareness emerges from neural activity, creating an inner experience that seems separate from the physical world, yet is intimately connected to it. The billions of neurons in your brain, each connecting to thousands of others, create a network of staggering complexity, more potential neural states than there are atoms in the observable universe. From this intricate dance of electrochemical signals emerges the unified experience of consciousness, your thoughts, feelings, memories, and sense of self. This emergence doesn't require any external force or substance beyond the physical brain. It arises naturally from the organization and activity of neurons. Just as the behavior of water emerges from the collective properties of HO, molecules that individually display none of water's characteristic properties, that the wonder of standing under stars, feeling both enclosed and infinite at once, captures something essential about our relationship with the cosmos. On a clear night, far from city lights, the sky presents itself as a vast dome, spangled with countless points of light. This celestial hemisphere creates a sense of enclosure, as if we stand within a great cosmic cathedral, its vaulted ceiling adorned with the glittering patterns of constellations. Imagine yourself in such a place, perhaps a high desert plateau or a remote mountain peak, where the air is clear and the horizon wide. Above you, the Milky Way stretches like a luminous river across the sky, its diffuse glow resolving into countless individual stars when viewed through binoculars or a small telescope. The longer you look, the more stars become visible as your eyes adapt to the darkness, revealing depths within depths, lights beyond lights. Consider how this perspective might relate to your own life path. Every choice you've made, every random event that has affected your journey, might have unfolded differently in parallel branches of reality. There might be versions of you leading vastly different lives, pursuing different careers, living in different places, forming relationships with different people. These alternate selves would be as real as you are, experiencing their own joys and sorrows, their own discoveries and disappointments, all stemming from the same origin but diverging through the accumulated effects of quantum branching. The many worlds interpretation doesn't require any change to the mathematical framework of quantum mechanics, simply takes the equations seriously, without adding the extra postulate of wave function collapse. This mathematical elegance appeals to many physicists, though others find the proliferation of unobservable parallel universes too high a metaphysical price to pay for this elegance as you continue to rest. Imagine these parallel universes not as distant places, but as alternate versions of reality that share the same physical space as our universe, separated only by their quantum states. Like radio stations broadcasting on different frequencies, these universes would occupy the same location but remain invisible to one another, their separate realities playing out without interaction or awareness of the others. The branch points between these parallel worlds would not be dramatic moments of cosmic significance, but the accumulated effects of countless tiny quantum fluctuations, the random decay of radioactive atoms, the precise path taken by photons, the quantum uncertainty in the position and momentum of particles. Each moment contains virtually infinite potential variation at the quantum level, creating an ever-branching structure of alternate realities, so numerically vast that it staggers the imagination. Some theorists have suggested that certain quantum phenomena, such as interference patterns in double-slit experiments, might be explained by interactions between parallel universes. The physicist David Deutsch, a prominent advocate of the many worlds interpretation, has argued that quantum computers derive their potential power from performing calculations in multiple universes simultaneously. These speculative ideas remain controversial, but they highlight how the concept of parallel universes has moved from pure philosophy to theories with potential implications. Imagine the quiet room around you filled with ghostly parallel versions of yourself, each slightly different, each following their own version of reality, all occupying the same physical space but forever separated by the unbridgeable gap between quantum states. Like ships passing in the night, these alternate realities would proceed on their separate courses, unaware of one another's existence, yet all stemming from the same fundamental equations, the same universal wave function that encompasses all possibilities. As you continue to rest and listen, imagine these other universes not as distant places we might someday visit, but as alternate realities coexisting with ours, separated not by spatial distance, but by more fundamental barriers, like parallel dreams occurring simultaneously in different minds. These universes would unfold according to their own internal logics, perhaps with their own conscious observers, wondering about the nature of their cosmic boundaries. Feel the gentle weight of your body, the subtle pressure where it meets the surface supporting you. This sensation of weight arises from the gravitational attraction between your mass and Earth's force that extends with diminishing strength throughout the cosmos. Every particle in your body is connected through this invisible force to every star and galaxy in the observable universe. In a very real sense, you are not separate from the cosmos, but intimately connected to it through these fundamental forces. The gravitational influence between your body and distant stars is vanishingly small, weak to measure with our most sensitive instruments, yet a gentle tether binding you to the farthest reaches of the observable universe. This connection is not merely poetic but mathematical, a direct consequence of Newton's law of universal gravitation and Einstein's general relativity. The stars and galaxies and nebulae you might observe in the night sky are not merely objects of beauty and wonder, but active participants in a cosmic web of mutual influence that includes you as one of its countless nodes, there is something both humbling and expansive about these multiverse possibilities. They remind us that reality may be far vaster and more varied than what we can directly observe. Like a listener catching fragments of many conversations in a crowded room, we may be perceiving only a tiny portion of a much richer and more complex reality. Our universe, vast as it seems, might be just one note in a greater cosmic symphony, one story among countless being told across the multitude of existence. The limits of our perception shape our sense of reality's boundaries. Consider how different the world appears to a bee, perceiving ultraviolet patterns invisible to human eyes, or to a bat navigating through darkness by echolocation. Our senses evolved to help our ancestors survive on the African savanna, not to perceive the full spectrum of cosmic reality. Our instruments extend these senses remarkably, allowing us to detect radio waves from distant galaxies or the subtle ripples, gravitational waves passing through Earth. Yet even these enhanced perceptions may capture only a fraction of what exists, like a person with a radio that receives only one frequency, missing the countless other stations broadcasting through the same space. Yet even if these other universes exist, they don't constitute an outside or beyond to our space in the usual sense. They wouldn't be located at some distant point we could reach by traveling far enough. They would exist in ways that transcend our usual spatial concepts. The boundary between our universe and others would not be a wall or an edge, but a more fundamental separation, a difference in the very fabric of reality itself. Rather than imagining space as a container that might have an outside, we might instead consider reality as a nested hierarchy of organizing principles, laws and patterns that give rise to the structures we observe. From quantum fields to particles to atoms to molecules to stars to galaxies, each level emerges from the one below it, creating new forms of order and complexity without requiring any external container or context. Consider a simple analogy. The rules of chess determine what moves are possible on the board, creating the potential for countless different games, strategies, and outcomes. These rules aren't located somewhere outside the chessboard. They're embodied in the very way the game unfolds. Similarly, the laws of physics aren't imposed from outside our universe, but are embedded within its very fabric. In the relationships between its parts, in the patterns of its evolution through time. The boundary of our universe, in this view, isn't a spatial edge, but the limits of applicability of these particular patterns and relationships as you rest. Imagine your consciousness as a similar kind of emergence, not something outside the physical world, but a pattern of organization that arises from the incredible complexity of your brain, like the multiverse emerging from more fundamental principles. Your awareness emerges from neural activity, creating an inner experience that seems separate from the physical world, yet is intimately connected to it. The billions of neurons in your brain, each connecting to thousands of others, create a network of staggering complexity, more potential neural states than there are atoms in the observable universe. From this intricate dance of electrochemical signals emerges the unified experience of consciousness, your thoughts, feelings, memories, and sense of self. This emergence doesn't require any external force or substance beyond the physical brain. It arises naturally from the organization and activity of neurons. Just as the behavior of water emerges from the collective properties of HO, molecules that individually display none of water's characteristic properties, that the wonder of standing under stars, feeling both enclosed and infinite at once, captures something essential about our relationship with the cosmos. On a clear night, far from city lights, the sky presents itself as a vast dome, spangled with countless points of light. This celestial hemisphere creates a sense of enclosure, as if we stand within a great cosmic cathedral, its vaulted ceiling adorned with the glittering patterns of constellations. Imagine yourself in such a place, perhaps a high desert plateau or a remote mountain peak, where the air is clear and the horizon wide. Above you, the Milky Way stretches like a luminous river across the sky, its diffuse glow resolving into countless individual stars when viewed through binoculars or a small telescope. The longer you look, the more stars become visible as your eyes adapt to the darkness, revealing depths within depths, lights beyond lights. Feel the cool night air against your skin, perhaps carrying the scent of pine or sage or desert dust. Listen to the subtle sounds of the night, the gentle rustle of leaves, the distant call of a night bird, the soft whisper of your own breath. These immediate sensory experiences ground you in the particular place and moment, even as your eyes and mind reach toward the cosmic vastness above. This simultaneous awareness of the immediate and the infinite creates a unique state of consciousness, a feeling of being precisely here, now, yet connected to the boundless reaches of space and time. The ancient Greeks called this celestial canopy the firmament, from the Latin firmamentum, suggesting solidity and stability. They imagined it as a crystalline sphere to which the stars were fixed, rotating around Earth with perfect regularity. This image of a cosmic dome persists in our language and imagination, even as our scientific understanding has revealed the true vastness of space throughout human history. Cultures have created myths and models to explain the appearance of the night sky. The ancient Egyptians saw the sky as the goddess Nut, her star-speckled body arching protectively over the earth. Norse mythology described the sky as the skull of the giant Ymir, with the stars being either sparks from Muspelheim or jewels set by the gods. Aboriginal Australians recognize the dark spaces between stars, particularly the dark nebulae in the Milky Way's celestial features, seeing them as spirit animals swimming in a heavenly river. These diverse cosmologies all attempted to make sense of the same visual experience, the appearance of a dome-like sky enclosing the terrestrial world. Yet simultaneously, we know that what we're seeing is not a dome or a ceiling, but a window opening onto almost unimaginable vastness. Each star is a sun, often larger and brighter than our own, separated from its neighbors by trillions of miles of empty space. The apparent closeness of the stars is an illusion created by our perspective, like distant mountains that appear to crowd together on the horizon, though we know they stand miles apart. Consider Betelgeuse, the bright reddish star marking the shoulder of Orion. This stellar giant shines about 550 light-years from Earth, meaning that the light now reaching your eyes began its journey more than 5 centuries ago. When Columbus was preparing to sail across the Atlantic, Betelgeuse itself is so vast that if placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, engulfing the inner planets, including Earth. Or consider the Andromeda Galaxy, visible to the naked eye as a faint smudge of light in the constellation of the same name. This spiral galaxy, similar in structure to our own Milky Way, lies approximately 2.5 million light-years from Earth. The photons now reaching your retina began their journey when our human ancestors were just beginning to use stone tools. And Andromeda contains roughly 1 trillion stars, each potentially hosting planetary systems with their own unique characteristics and possibilities. The light from these distant objects carries information about their nature and history, their chemical composition, their temperature, their motion through space. Astronomers can analyze this light, breaking it into its spectrum of wavelengths, to determine what elements are present in distant stars, whether they are moving toward or away from us, whether they are surrounded by planets or dust disks. This analysis transforms the aesthetic experience of stargazing into a scientific investigation, revealing the physical nature of these distant lights without diminishing their beauty. As you gaze at these distant lights, you're looking not just across space, but back in time. The universe presents itself to us as a kind of living museum, where the light from distant objects carries information about how they appeared in the remote past. The most distant galaxies visible to our most powerful telescopes appear as they were billions of years ago, when the universe was in its adolescence, and many of the elements necessary for life had not yet been forged in stellar furnaces. This relationship between distance and time in astronomy creates a unique kind of temporal perspective. The farther away we look, the further back in time we see. The nearest star beyond our Sun, Proxima Centauri, appears to us as it was about 4 years ago. Stars at the center of our galaxy appear as they were about 27,000 years ago. The most distant observable objects, near the edge of the visible universe, show us light emitted nearly 13.8 billion years ago, shortly after the Big Bang itself. This telescoping of time creates a cosmic panorama in which we see different epochs simultaneously, as if we could observe dinosaurs roaming the distant horizon while birds, their descendants, fly overhead. This dual experience of enclosure and infinity, of boundary and boundlessness, reflects something fundamental about human consciousness. We navigate the world through boundaries and categories, dividing continuous reality into discrete objects and regions. Our perception naturally creates distinctions between figure and ground, self and other, inside and outside. These boundaries help us make sense of experience, allowing us to identify patterns, predict outcomes, and navigate our environment. Our brains evolved to parse the world into manageable units to distinguish predator from prey, edible from poisonous, kin from stranger. This categorical thinking served our ancestors well, allowing them to make quick decisions in environments where hesitation could be fatal. We inherit this tendency to draw boundaries, to create mental maps with clear territories and borders. Languages reinforce this tendency, dividing the continuous spectrum of color into discrete names, the fluid transition of time into separate tenses, the interconnected web of life into distinct species and categories. Yet, we also sense the artificiality of these divisions, the underlying continuity that connects all things. At the atomic level, the boundary between your body and the air around it becomes blurry, a region where gas molecules interact with the atoms of your skin, where heat and moisture transfer occurs, where the distinction between you and Natu loses its sharp definition. Similarly, at the social level, you exist not as an isolated individual, but as a node in a complex network of relationships, each shaping and being shaped by the others. Modern science reveals the continuity beneath apparent boundaries in countless ways. The discrete species of Linnean taxonomy give way to the continuous variations of population genetics. The seemingly solid matter of everyday objects dissolves into mostly empty space, populated by probability clouds of quantum particles. The apparently distinct forces of nature, gravity, electromagnetism, the strong and weak nuclear forces may be unified at high energies, different aspects of a single underlying interaction. Even the boundary between life and non-life becomes less definite when we examine viruses, prions, or the complex organic chemistry that may have preceded the first living cells. Indigenous cultures often express this dual awareness through myths and practices that honor both the structured and boundless aspects of reality. Many Native American traditions, for instance, conceive of the sky as Father Sky, complementing Mother Earth, a sacred enclosure that both shelters and transcends the earthly realm. The Lakota phrase, mitaku, oyas, I often translated as all my relations, or we are all related, expresses the profound interconnectedness of all beings within this cosmic enclosure. This phrase appears in many Lakota prayers and ceremonies, acknowledging kinship not just with other humans, but with animals, plants, stones, and stars. It recognizes that boundaries between categories of being are permeable, and that relationship extends beyond the visible or immediate. This perspective doesn't erase distinctions. Human is not a stone, is not a star, but it places these distinctions within a larger context of fundamental unity and interdependence. The Navajo hogan, a traditional dwelling with its door facing east, replicates in microcosm the structure of the cosmos as understood in Dine Navajo tradition. The circular or octagonal floor plan mirrors the perceived circularity of the horizon, while the smoke hole at the center of the roof creates an axis connecting earth to sky, allowing communication between realms. In this worldview, human dwellings don't simply exist within the cosmos, aligning human life with cosmic patterns. The hogan exemplifies how traditional cultures often create physical spaces that embody their cosmological understanding. The dwelling becomes not just shelter, but a model of the universe, orienting its inhabitants within the larger cosmic order. The cardinal directions take on symbolic significances associated with dawn and beginnings, south with warmth and growth, west with evening and reflection, north with night and wisdom. By aligning human habitation with these cosmic directions, the dwelling creates a lived experience of cosmic belonging, a tangible reminder of humanity's place within the larger order. Similarly, Aboriginal Australian songlines map the landscape through story and song, creating meaningful pathways through what might otherwise be experienced as boundless, undifferentiated space. These songlines trace the journeys of ancestral beings who shaped the land during the Dreamtime, the creative period at the beginning of the world. By singing the songs associated with these pathways, Aboriginal people not only navigate the physical landscape, but also maintain their connection to the ancestral past and the cosmic order. The songlines demonstrate how meaning and navigation can be encoded in narrative rather than abstract cartography. Rather than representing the land as an objective, geometric space viewed from above us in modern maps, the songlines embed direction and distance in stories that must be remembered and performed. Specific features of the landscaper: distinctive rock formation, a waterhole, a stand of trees become mnemonic anchors for these narratives, allowing precise navigation across vast distances through seemingly featureless terrain. These indigenous cosmologies often lack the sharp distinction between natural and supernatural that characterizes much of Western thought. Spirits, ancestors, and cosmic forces aren't separated from the physical world by some absolute boundary. Rather, they interpenetrate it, becoming more or less perceptible depending on circumstances, awareness, and ritual context. The boundary between visible and invisible aspects of reality remains permeable, shifting rather than fixed. Many indigenous traditions describe reality as having multiple layers or dimensions, all present simultaneously but not equally accessible to ordinary awareness. Through dreams, visions, or ritual practices, individuals might temporarily access these other dimensions, gaining insight or healing not available through everyday perception. This multi-layered view of reality bears interesting parallels to modern scientific concepts of multiple dimensions or parallel universes, though expressed through different conceptual frameworks and serving different cultural purposes. Knowing that the stars overhead are suns like our own, that many harbor planets, that light from the most distant visible objects has traveled for millions or billions of years to reach our eyes. These facts deepen our appreciation of the night sky. We stand at the boundary between the terrestrial and the cosmic, between the familiar scale of human experience and the vast scales of astronomical space and time. Modern astronomy has revealed that our solar system resides in a spiral arm of the Milky Way galaxy, roughly 2/3 of the way from the galactic center to the outer edge of the luminous disk. Our galaxy contains between 100 and 400 billion stars, arranged in a flattened disk about 100,000 light-years across, with a central bulge and halo of older stars surrounding the disk. From our position within this vast stellar community, we see the combined light of billions of stars as the luminous band of the Milky Way stretching across the night sky. Our particular spiral arm, called the Orion Arm or local spur, is a relatively minor feature compared to the galaxy's major spiral arms. We orbit the galactic center at a speed of about 828,000 kilometers per hour. Yet, even at this tremendous velocity, a single orbit takes roughly 230 million years to complete. The last time our solar system was in its current galactic position, dinosaurs had not yet evolved on Earth. By the time we complete another orbit, Earth's continents will have shifted position, and many of our current species, perhaps including humans, may have given way to new forms of life, despite its impressive scale. Our galaxy is just one among billions in the observable universe. The nearest large galaxy to our own Andromeda is on a collision course with the Milky Way, though the actual merger won't begin for about 4 billion years. When these two spiral galaxies eventually merge, they will likely form a giant elliptical galaxy that astronomers have whimsically named Milkomada. Any observers alive on Earth at that time would witness a night sky dramatically different from our own, with the Andromeda galaxy growing ever larger until it fills much of the visible sky, its stars eventually mixing with and becoming indistinguishable from those of our own. Galaxy. Beyond our galaxy lies the local Grupa collection of about 80 galaxies bound together by gravitational attraction, and beyond the local group extends the Virgo supercluster, a vast assembly of galaxy groups and clusters spanning about 110 million light-years. Recent astronomical surveys have revealed even larger structures, vast filaments and sheets of galaxies surrounding nearly empty voids, collectively forming a cosmic web that spans billions of light-years. This cosmic web represents the largest known structure in the universe, a network of interconnected filaments composed of dark matter and luminous galaxies. The filaments surround enormous voids, regions of relatively empty space that can span hundreds of millions of light-years across. This foam-like arrangement of matter on the largest scales appears to have originated from quantum fluctuations in the earliest moments of the universe. Tiny variations in density that were stretched to cosmic proportions by inflation and then amplified by gravity over billions of years of cosmic evolution. As you continue to rest beneath this imagined canopy of stars, feel the gentle pull of gravity, the force that both binds us to Earth. Every particle in your body experiences this subtle attraction to every other mass in the universe, from the nearby ground beneath you to the most distant galaxies at the edge of the observable universe. The weight you feel is actually the result of two opposing forces: the gravitational attraction between your mass and Earth's, pulling you toward the planet's center, and the electromagnetic repulsion between the atoms of your body and those of the surface beneath you, preventing you from sinking through the floor. This balance of forces, gravity pulling inward, electromagnetism pushing outward, creates the sensation of weight, the feeling of being simultaneously attracted to Earth and supported by it. Gravity's influence extends across cosmic distances, acting instantaneously according to Newton's law of universal gravitation, or propagating at the speed of light according to Einstein's general relativity. Either way, it creates a web of attraction that encompasses all matter and energy, binding the cosmos into a unified whole. Despite the vast empty spaces between celestial bodies, Einstein's general relativity revealed that gravity is not actually a force in the conventional sense, but the curvature of space-time caused by mass and energy. Massive objects like stars and planets create depressions in the fabric of space-time, and other objects move along the curved paths determined by this geometry, like a marble rolling around a depression in a stretched rubber sheet. Earth orbits the Sun not because of a mysterious attractive force, but because it follows the path of least resistance through curved space-time. This gravitational embrace is asymmetric in an important way. While electromagnetic forces can be either attractive or repulsive positive, charges attract negative ones, but repel other positive charges. Gravity, as we understand it, is always attractive. Masses always draw other masses toward them, regardless of composition, charge, or other properties. This purely attractive nature means that gravity's effects accumulate across cosmic distances without being cancelled out by opposing forces. The stars will shine long after we are gone, their light crossing endless space. But tonight, they shine here with you in silence. May your evening be calm and your rest be deep. Whatever dreams may come, may they carry you gently through the night, cradled in the vast and tender embrace of a universe that has no edge, no boundary, no final shore, only the endless unfolding of wonder itself.